All right, so let's start our group discussion here of the questions from this analysis paper. I think that this paper is sort of a very good example of the types of things that you see in sort of the domain literature. There's obviously constraints on the number of words you're allowed to put in a paper, and I think what you see gets really compressed is the amount of detail about the statistical analyses that were done. So in this example, in this paper, you can see that if you want to figure out exactly what was done, you have to kind of make some assumptions and kind of read between the lines in terms of what was said, because authors can't always spend all the space that they need to say, well, for this particular comparison, we did exactly this, and we did a two-sample t-test, two-sided, blah, blah, blah. So you have to kind of read a little bit and read into what was done and make some assumptions in order to kind of make sense of these kinds of papers. All right, so let's kind of go through the questions here. First question, the paper uses data from 7 annual surveys ranging from 2003 to 2009. And despite the fact that this is data from multiple surveys over time, the authors don't say anything about correlation and don't deal with any sort of type of correlated data at all. They just sort of assume that all the observations are independent. So why do we think that's reasonable? What is it about this setup that makes it reasonable to assume that the observations that they have in their data set are independent? Yeah. Yeah, so that's really the key thing, right? So when you look at the way that ATUS was designed, they take a sample of several thousand people in any given year, but as they move on to the next year, they grab another totally different sample of people. So they don't go back to the same people that they sampled in 2003 for 2004. They take a totally new sample of people in 2004. Then in 2005, they take a totally new sample of people, et cetera, et cetera. So what you've got is, yes, you have information accruing over time, but it's not on the same individuals. So, so what assumption are they making here by combining data across 2003 to 2009 in terms of sort of homogeneity? So if somebody said, well, I'm going to take data from 2003 to 2009, and I'm just going to sort of throw it all in together, right? What are they sort of implicitly not saying? We don't have to worry about what?
People are living the same way.
Right, exactly, right. So in some sense, the patterns that we see reflected in the 2003 data are going to be similar to the patterns that we see reflected in the 2009 data. So there hasn't been some big shift, some big cultural shift that has changed the dynamics of how people spend their time over that period. Right now, if you started to expand this and say, well, we're going to use all the data from the early 1980s up until the current day, well, then maybe you'd have some concerns. There could be some pretty big differences between the ways people spend their time in the early 80s and the way they spend their time now. And so sort of combining everything together might not give you a very good picture of what goes on. But in this relatively narrow time period, the implicit assumption is that more or less we're combining data that are sort of similar relative to time spent, et cetera, and the way that people behave. So clearly, if we had a different design and we decided to sample a set of people in 2003 and then to go back to those same people year after year after year to see how their time use was different in those different years, then we'd have what's called a longitudinal study, and we'd have to worry about correlation. We'd have to go to techniques that are beyond the scope of this class. But that was not done here. This is just for every year, we just take a different sample of people, and as long as we're comfortable lumping those years together, right, then we're okay with assuming independence. All right, so I'm doing the super fancy, low-tech reveal, as we go through. So I'll post these sort of answers on the course webpage.
Question for you, Joe.
Yeah.
Is it like, are they just going out of the way to remove the people that were previously sampled from the sample pool? So, for example, like I could randomly select 5 people in here. Like, oh,
Sure.
People, but
I don't know exactly how they handle the detail. It's pretty unlikely if you think about it. I mean, if they're sampling a few thousand people from essentially the entire U.S. population, then the likelihood that you have overlap from year to year is very, very small. Now I don't know. You'd have to go back and look in detail at their sampling plan to say, like, if you were included in the previous survey, do you get excluded automatically from getting done in the follow-up survey?
Because
My-
that
my-
would help with the independence thing, because everyone has to have an equal chance of
Right,
being enrolled.
right. So my guess is that they probably don't exclude people if they've previously participated, just because, yeah, maybe a couple people it'll happen with, but you don't really care about the dependence if you've got a couple people up to show up in a couple of the surveys. It's really you worry about if you have, everybody's got repeated surveys, then you have a concern. But in this case, since it's a general population sample, we're sampling a very small fraction of the U.S. population in any given sample. We're not too worried about overlap. It might happen, but it'll be rare. Okay, so what's the data going to look like, right? What's the data set going to look like? Just to sort of think about a basic schematic, right? So if we had like an Excel file representing these data, what do we think it would look like? So what columns would we think we'd have in a data set that we'd use to analyze to do this analysis?
Identifier.
Okay, it's probably an identifier. All right. I mean, not strictly speaking, right? Do we actually need an identifier?
As long as you know that it's they're each independent, like there's no duplicates.
Right. So yeah, it's probably good for data quality checking purposes to have an identifier. But if you knew that you had a unique, every row of your data set was a unique individual, you wouldn't necessarily use the identifier for anything. Okay. So identifier. What else? What else are you going to need?
Word category.
Okay. Word category. So that's what type of variable is that going to be?
Would be
Yeah, so it's like a categorical variable, so it's going to have those 4 levels, right? Sedentary, light, moderate, vigorous. All right, what else?
Age and gender.
Age, so a bunch of demographic information, age, race, etc. Okay. What about the time use? How do you think the time use variables are going to be coded? How are they going to appear in our data set?
Intensity of leisure activity.
Okay, so let's just go quickly here and look at the paper itself. So we've got, household income is another one, of course. So we've got these various categories here. We've got at work, sedentary, light, moderate, vigorous, sleep, unidentified. So how are those how are those variables going to show up in the data set, right? So are we going to have one column representing, category of activity, or are we going to have multiple columns, one for each of those categories? What do you think how's that going to actually show up in the data set?
well, if we had an identifier, and you have multiple rows within one column, but otherwise you need multiple variable columns. So
Okay.
for each of-
Okay, so if we wanted to have one row per individual, right, and we didn't want to have multiple rows, what would we do? How would we implement that? Like, what variables would actually show up in your Excel spreadsheet, and what would their value types be?
Would it be by activity, so like gardening or cleaning or running? So you have like a ton of variables.
Possibly, right? So it's certainly possible that you might start with that very wide data set, which broke it down into these very detailed categories.
Wouldn't it just be sedentary, light, moderate?
Yeah, so the other thing you could do is you could aggregate up to these activity categories, and then you'd have a variable that represented time at work, time doing sedentary activity outside of work, time doing light activity outside of work, time doing moderate, and each of those would have a number of minutes in it. So you'd have variables corresponding to each of those activity categories, and each of those variables would report a number of minutes in each of those categories. Okay, so this actually, the structure of the data set that you would probably use to do this analysis is quite similar to the structure of the data set that you're going to have access to, right? That I posted, where you've got a bunch of demographic information, and then the time use are broken down. The time use is broken down into a number of categories, and you're given the number of minutes within each of those categories that people spend. Okay. So I don't have a fun reveal for that one. Okay, so figure 1 reports the estimate plus or minus the SEM for time spent in various activities. So this is very common for people to report plus or minus the standard error of the mean. So why are the SEM so small here in this study? Yeah, so the sample size is huge, right? There's like 30,700 people in the sample size. So what's the formula for the SEM? Right, so it's the standard deviation divided by the square root of n, right? So the square root of n is huge, which means that even if your standard deviation is fairly big, you're dividing by this huge number, and so you're getting really small standard errors of the mean, which means that we have a lot of precision for estimating the mean amount of time spent in each of these activities, right? That's the whole point of this pie chart. Pie chart was down here. Yes. Right, what we learned from this pie chart, right, we certainly can see the breakdown. By the way, I'm not a big fan of pie charts, so there's probably improvements that could be made here. But what this is saying is that the estimated mean amount of sleep was 465.7, and that's a very precise estimate, okay, because there's not a lot of uncertainty around what that mean value is. So if we wanted to compute a confidence interval for the mean amount of sleep, all right, what is the confidence interval that we get? Right. So you're going to get 465. Is it 456? 465.7 plus or minus, and where does the 1.2 come from? 1.96 times the standard error of the mean, right? That's the standard confidence interval formula. So from this standard error of the mean number, you can go directly to a confidence interval, okay? And why are we comfortable using 1.96 here as opposed to having to use like a t quantile? Yeah, sample size is huge, right? So no issue. You know, we could do a t statistic with 30,757 degrees of freedom, but I bet you that number is going to be very close to 1.96, right? So we're going to use 1.96, and we're very comfortable with that. What about the standard deviation of amount of sleep? What do we get for that? So you said 0.77, 105. All right, so let's think about that. Which of those numbers makes more sense? So does 0.77 make sense? And what you'd be saying is that the standard deviation in the population of amount of sleep per night is 0.77 minutes, which would mean that the entire population, about 95% of the population, should fall between 463 minutes of sleep and 469 minutes of sleep. That seems unlikely, right? So you need a bigger number. 105 is correct. So how did you get to 105? That formula. Okay.
Standard deviation is equals to standard error times square root of sample size.
Right. So the SEM is the standard deviation over the square root of n. Okay, whoops. Sorry, 1 second. We were supposed to reveal that before. Let's get this back here. Okay. So there's your confidence interval. The standard deviation is the standard error of the mean times the square root of the sample size, because of this formula up here, which is the SEM is equal to the standard deviation divided by the square root of n. So you can recover the standard deviation as well from that standard error of the mean. All right. So it's always good, when you look at these statistics, don't feel like you're constrained necessarily by the number that they're giving you. If you want a different number, you feel a different number would be interesting, like you'd like to know the standard deviation, you should try to compute it from what's given. Okay? In this case, you can, and you get approximately 105 minutes, which sort of makes sense if you think about it, because plus or minus 2 standard deviations is about plus or minus 200 minutes. So that says about 95% of the population is going to fall between 465 minutes of sleep plus or minus 200 minutes. So 200 minutes is what, like 3.5 hours? So 465 minutes is 7.5 hours, so 7.5 hours plus or minus 3.5 hours. That seems reasonable to contain about 95% of the population, right? So it's always good to do that sort of sanity check to make sure that the numbers make sense. Okay. Question 5. Table 1 reports mean plus or minus standard deviation for age, but N% for household income and for race ethnicity. Why? I know you guys know the answer.
Age is not a categorical.
Okay, so what kind of variable are we viewing age as? Okay, okay. So what about household income here? So household income, is it inherently a categorical variable? Not necessarily, right? I mean, we could view household income as a continuous variable if we wanted to, right? We could simply say in number of dollars, it's essentially continuous for household income, but we decided to make it into a categorical variable, right? So when you make something into a categorical variable, does it make sense to compute a mean and standard deviation? Probably not, right? You know, maybe for household income, you could sort of rig something up, but of course it doesn't make any sense to take the mean race or ethnicity or the standard deviation of race or ethnicity. Those don't make any sense. So it's very conventional to do what is done here in this table 1, which is that you decide, when you decide to summarize your variables, which variables are going to be viewed as continuous variables and which variables are going to be viewed as categorical variables. And for the continuous variables, you're going to report some central tendency measure, usually the mean, sometimes the median, and then some measure of spread, in this case the standard deviation. For categorical variables, you're going to report N%. So it's very, very common to see a table where the way that you interpret the entries depends on whether the variable is continuous or categorical. And you'll report mean standard deviation for the continuous and N% for the categorical. Okay, so this is very commonly seen in papers, a very common thing to do. Magic. All right. Okay, so now we get to the, if you want, the sort of digging into the nitty-gritty of what was written and try to translate that into what was actually done. So the first sentence of the footnote below table 2 is, not significant p greater than 0.05 differences in age by work category indicated by common exponent letters are indicated by common exponent letters for total sample, males and females. All right, so I'm going to go over to that table so we can see what that's referring to. Okay, let's see if I can, maybe that's a bit too big. All right, so here's that sentence. Okay, so what is that sentence saying? What does that mean in terms of the table? So which column are we referring to here in the table? So it's the age, comma, year column. So which entries have common exponents? Well, these two, oops, light and moderate here for the total sample, light and moderate here for the male subgroup, and light and moderate here for the female subgroup. All right. So the sentence says, not significant differences in age by work category are indicated by common exponent letters for each of these groups. So what does it mean if we just take the total group here? What does it mean that the light and moderate work categories have the same, that same A superscript? Okay, so that means if we compared the mean what? The mean age, right, between the light and moderate work categories in the total group, okay, that test did not give a significant result. What does that imply about the, so, okay, now sedentary and light don't share a common exponent, right? Sedentary and vigorous don't share a common exponent. Moderate and vigorous, moderate and sedentary, those don't share a common exponent. So what does that mean about those comparisons? Right. So I'm presuming here, and again, this is my interpretation of what was done, that they performed pairwise tests to compare all the different pairs of work categories, and they got p-values for all those comparisons. And what it means is they said all those comparisons were significant, except for the comparison between light and moderate, where there was no significant difference. All right. So let me add a question here, which is, do you think that this is relevant? Well, or scientifically, is it scientifically interesting that that the only two categories that were not significantly different were the light and moderate groups? And if you're shaking your head no, why not?
Sensitization of what applies.
Okay,
Sort of activities.
sure. So there's totally debate of what these categories are defined as, right? So is that a meaningful difference? But what about something related to the way that the study's been set up itself, or the way that the analysis has been set up itself? So maybe we can see this a little bit better by looking at maybe let's look over at the at work category here, right? So if we look here at the at work category and we look within males, for example, we see here that this number here, this row, the sedentary group and the light group, they don't share a common exponent, right? Which means that those differences are potentially significant, right? But what's the actual difference in minutes spent at work between those groups? 3 minutes, right? So why do we think that we can find a difference of 3 minutes being significant?
Sample size.
Right, the sample size is huge. So we have to be very careful in situations like this where we have such a big sample size. Oftentimes, everything under the sun is statistically significant, right? Because even tiny, tiny differences in means are going to look statistically significant because, as we know, the sampling distribution of X bar, right, gets really, 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 really narrow. And so you can distinguish means that are very, very close together if your sample size is very big. But the question is, just because because two groups are statistically significantly different, doesn't mean you care about that difference. All right, so there's a lot of significance here in terms of statistical significance, but it's not, you have to be careful about deciding whether or not there's a scientifically meaningful difference that you're seeing between these groups. Okay? Okay. So now let's look at the rest of the bullets in this footnote. So what type of statistical tests do you think are being done here to report these bullets? Well, let me back up for a second and ask, do the authors tell you explicitly what tests are being done here? No, because hopefully we wouldn't all be confused if the authors had already said, yes, these are the kind of tests we're doing. So you have to read between the lines a little bit. First piece of evidence that you can bring to bear on trying to figure out what kind of test is used here is what outcome is being compared for all these tests. What kinds of outcomes?
Is it difference?
Yeah, it's a difference of time spent, mostly, except for that difference in age, right? So what kind of outcome variable are we comparing here? Is it a categorical variable or is it a continuous variable? It's continuous, right? So we're either viewing age as a continuous variable or time spent at work, or time spent in sedentary activity, or time spent in light activity, etc. So in all these cases, we're comparing continuous variables. So when we're comparing continuous variables, what are we generally comparing about continuous variables? What characteristic of those variables, what characteristic of the distribution are we generally comparing? The mean, right? So we're doing a comparison of means. What kind of tests do we know for doing comparisons of means? Pretty much just the t-test, right? So based on what we know in this class, you can pretty much assume that what they're doing here is doing a whole bunch of t-tests, all right? Now, you mentioned pairwise t-tests. I mean, you have to be a little bit careful between pairwise and pair t-tests, which are not the same thing, right? You're correct. It is a pairwise t-test. Pairwise just means we're looking at a whole bunch of different pairs of groups and doing 2 sample t-tests between those groups, right? So these are almost all, I think they're all 2 sample t-tests, okay, comparing the various groups that are being stated. So for example, when it says no sex differences in age by work category, my interpretation of that is that they are looking at sedentary males who are in the sedentary work category and comparing their mean age to the mean age of females who are in the sedentary work category. They're doing a 2 sample t-test to compare those means, and they found that that p-value was not less than 0.05, so there was no significant difference. Then they're going to the light males, light females, comparing, finding no significant difference, etc., for each of the categories. Okay? When they look at time spent at work, and they say that male is greater than female for all work categories, well, what they're probably doing is they're comparing 469 to 433.9. They're doing the 2 sample t-test, right? They're saying that's significantly different. Hardly surprising given that the standard error of the mean is 2.1, so there's clearly a lot of non-overlap here between the confidence intervals. And then they're doing the same thing for light versus light, moderate versus moderate, vigorous versus vigorous. And they're saying each of those comparisons was statistically significant, p less than 0.05. In fact, p less than 0.0001, again, not surprisingly, because these are fairly substantial differences compared to the amount of uncertainty we have in our ability to estimate these numbers. And so that's the result that they report. Okay, so all these bullet points refer essentially to 2 sample t-tests, right, comparing various groups against each other. All right? So what concern might you have about making conclusions on the basis of all of these statistical tests? Okay, so there's the problem that we mentioned before, which is that just because differences are statistically significant, you have to still decide whether or not they're scientifically meaningful. There's another concern you might have as well. So how many tests are being summarized here in these bullet points? Yeah, a lot. I don't know exactly how many it is, but it's, if you figure, we said for like time spent at work, that was 4 separate tests, the sex differences of 4 separate tests, and there's 7 bullet points. There could be 30 or 40 different statistical tests here that are being reported, right? Now, when you do 40 hypothesis tests, even if there's no difference between groups, and you use a p-value of 0.05 as your threshold, about how many tests would you expect to show up as being statistically significant out of 40 if you did 40? So you'd expect about 2 out of 40, right? 1 out of 20 to show up. So there is some concern about the multiple testing problem here, because we've done so many statistical tests that we do have to be aware of the fact that we've done this many tests when we're interpreting these p-values.
So what is would they give you those p-values?
Right.
So we're assuming that they're not doing each paired test separately and then getting a p-value for that, in which case it's not really multiple comparisons?
Well, it depends on what they're doing. Yeah. So if they are doing ANOVA, then they would get a single p-value. But for example, here they say time spent in sedentary outside of work, male greater than female, all work categories, all p less
Right.
than 0.02.
Right,
So that
that's
sort of
why I say
implies
that
they're
in
doing
some.
all the pairwise. I assume they're doing all these things. They're doing all pairwise, and they're saying all of them were below that threshold. Now, I personally hate when you say like all p less than 0.02. Well, that includes 0.019 and like 0.00001. But it's actually fairly conventional for people to do that. I happen not to like it. But what makes you a little bit less worried about the multiple comparison problem here?
They're still really-
Yeah, the p-values are really tiny. So even though you've done multiple testing, it's not like you're kind of on the borderline where it's like, well, do we need to worry about this borderline thing? The p-values are really, really small. So even if you were to account for the fact that you've done all these multiple tests, you probably would still have significant results. But again, that raises the issue of just because something's statistically significant doesn't mean it's scientifically meaningful, maybe not. All right. Ways to do figure 2 better. What do we dislike about figure 2? Maybe you don't dislike anything about figure 2. Yeah. So what would that help with?
It's just options of grades, it's one more hard to do.
Yeah, I agree. I think it's very hard. I mean, you look at the top, the big gray bar at the top and the smaller gray bar at the bottom, and it's kind of hard to distinguish those shades, especially. Yeah, I think I would definitely agree with you there. There needs to be some better way of differentiating the bars. What else?
We haven't talked about the fact that they all pretty much look about the same, the way this is represented.
Mm-hmm.
If they're trying to make a point, unless they're trying to make a point that they're all the same, which they're kind of not based on the discussion,
Right.
it's not illustrating that.
Yeah, I think that's fair. It's sort of, you need to think a little bit about what's the purpose, right? What are you trying to show here? And if they're trying to show that these are different, they're really not accomplishing it. And if they're trying to argue that they're the same, then you sort of wonder, do you really need a figure to show that? Other complaints? I personally think the text is too small. Certainly the numbers on the plot, I think are very small and sort of hard to read. And if you're going to be putting those numbers anyway, I think you could put them in a table. Anybody have any thoughts about the ordering of the categories here? The ordering of the stacking? I personally thought it was a little weird to have like sleep and then work and then vigorous and then moderate. I mean, it seemed like a very odd ordering to me to have like sleep, which is in some sense the most sedentary activity, be before work, but then you had vigorous and moderate and light and sedentary. It seemed just a sort of a strange ordering to me. And I'm not sure that there's a correct ordering here, but that just struck me as being a little bit of an odd choice. So, there might be better options here for figure 2. All right. Maybe this isn't so much how could figure 2 be improved, but what do you hate about figure 2? All right. So the second paragraph of the discussion has a bunch of percentages in it, but there's no inference reported. What if we wanted to do inference about those percentages? So first question is, if I gave you this paragraph, could you actually give me confidence intervals and p-values on the basis of this paragraph? So if I said I want confidence intervals or I want p-values comparing groups, on the basis of the percentages that are reported in this paragraph, could you actually do that? Is there enough information? Yeah, there is, right? Because you only need 2 pieces of information, right, to do inference about a proportion. What do you need? You need the estimate of the proportion, and what else? Sample size. That's it, right? So you know the sample size. They give you the estimate of the proportion. So if I said, I want to know, so I said, okay, approximately 39% of the total sample engaged in 91.6 minutes of moderate to vigorous intensity activity outside of work on the day queried. Well, if I wanted to say I want a confidence interval for that 39%, right? How would we calculate that? So what's p hat in this case? It's just 0.39, right? 39%. So p hat's 0.39, right? We can calculate the standard error, right? P hat times 1 minus p hat over n, take the square root of that, right? And then we do p hat plus or minus 1.96 times that value. That's going to give you a confidence interval. You can always transform back to percentages by multiplying back by 100 at the end, right? So we could compute confidence intervals for each of those numbers, all right? Now, what if we wanted to compare, for example, for that 39% number, what if we wanted to compare the percentage of people who were engaged in this 91.6 minutes of moderate to vigorous intensity activity outside of work? We wanted to compare it between men and women. What would we do? What test do we know how to do for that? So there's two kinds of tests that we could do. Yeah, well, it's not a t-test. It's sort of a z test because it's a difference in proportions, right? Because we can look at a difference in proportions, p1 hat minus p2 hat. We can compute the standard error of that difference, right? We could do a hypothesis test for this difference in proportions, or as some people mentioned, we could do a chi-square test, right? Any reason to do a Fisher's exact test here? No, right? Sample size is big. We believe in the central limit theorem. We've got plenty of people in every cell. We don't need to do any kind of exact test here. We could if we wanted to, but it's not necessary. All right. Any questions about this? What we've discussed? Whoops. Oh, that's small. That document is going to be up. It will. Okay, so what I'm going to suggest is if you have not had a chance to get together with your group and talk about sort of questions for the data analysis project, you have another 20 minutes or so where you can work with your group to talk about that. But remember, Friday, 11:59 p.m., we want you to submit a couple of ideas that you have. We'll try to turn those around by Monday. Over the next couple of days, I'll put up a document about what we're sort of expecting out of you from the statistical analysis plan, but we'll probably also spend some time next week in class talking about what goes into a statistical analysis plan and also spending some group time as well in class. Sound good? Yeah.
So only one person needs to submit.
Yes. So the way it's set up is we've actually set up the groups in Moodle such that if one person submits for the group, then it shows up as a submission for everybody. So yeah, only one person needs to submit. So it's always good to discuss who's going to be the designated submitter.
Yeah, no, that's fine. We already have.